I want to impress upon you that this is a fake LC circuit, and that we are going to say it's done in such a way that there is no resistance in the LC portion of the circuit. And at the very end of our conversation, we will add back resistance in the circuit, and you'll understand why we had to leave it out. So let's start by understanding what an LC circuit looks like and what we're going to do. To utilize the LC circuit, what I would like to do is charge up the capacitor first. Thus, I have a switch 1 that I can close while switch 2 is open. This will allow the capacitor to fully charge. And then when the capacitor is charged, I will open switch 1 and close switch 2. So time equals 0 actually is going to begin the moment switch 2 is closed. So we start this by closing switch 1 and wait long enough for the capacitor to come to full charge. It'll come to full charge when our applied EMF is the same as the voltage across the capacitor. With no resistor in there, this should take place very quickly. It'd be limited only by the size of the capacitor and whatever internal resistance is in the battery. So after a long time has passed, which is probably just a couple of seconds, we will open switch 1, and then at t equals 0, close switch 2. Let's observe what's going to happen. And by observe, I mean let's draw a Kirchhoff's loop and see if we can predict the nature of what an LC circuit will do. So we're going to start by recognizing that in this loop there's going to be the voltage drop across the capacitor, which although its initial boundary condition will be E0, we know that's only going to stay there for an instant. There's a future condition where probably its energy is going to go down, and that means its voltage will go down. And then we'll have minus EL, the potential difference across our inductor, and that has to equal 0. Now we're going to put in what we know about these things. This is going to be Q over C, and this is going to be L di dt. All good? Now, this is a differential equation, but it's a differential equation in current. And I have charge there, and I do know that there's a relationship between charge and current. In fact, that relationship also is a differential. So it seems to me that through a little bit of substitution, we could render this equation as a full differential equation in terms of Q. Now, if you've already had a course in mechanics, this will be very familiar to you. Well, it'll be vaguely familiar to you. If you've never had a course in mechanics, then you probably have not seen this before. And if you're an AP1, we didn't do this. But this would be written as a double derivative. And there's a way to write that. This is just symbology because the symbols don't mean very much. But you would write it as d squared q over dt squared. And it's symbology because that doesn't make a lot of sense. The d isn't actually squared in the numerator. It's just saying that it's the second derivative of charge with respect to time, and that we're relating it directly to charge. This is a second-order differential equation, and a second-order differential equation cannot be solved by splitting a derivative. So we can't isolate this derivative, multiply both sides by dt squared, and think that we can do two integrals and that will fix it. That's not how this goes. This requires a course in differential equations to learn some of the ways in which you can take a differential equation and solve it. And some of you are going to get some of that, I think, towards the end of BC, but most of you probably won't get it until after you've taken Calc 3 and then you take a course in differential equations, Diff-EQ. And even some of you who are exceptionally bright might go on and take a partial Diff-EQ class, which you start getting into real mysterious kind of stuff when you start taking partials. But all of you will probably, if you go into any kind of STEM class, will probably take Diff-EQ. So first chapter of any good differential equations book, and I've got one over there, is guess. That is the first chapter of any good differential equation. Is just a guess. Guess at your answer. So that's what we're going to do. We're going to guess at our answer. And to do that, I'm going to isolate the differential completely. It will make doing this easier. So what am I doing? I want to go. There we go. So what we want is Q as a function of t. Because if I can get charge as a function of t, I can get potential as a function of t, and I can get current as a function of t. So I moved the differential to one side, and I divided both sides by L, and I separated out Q because Q is the important variable here. Now, if you read this, it says that if I have a function for Q is a function of t, and I take the derivative twice, I will get back the original function, I'll get a negative sign, and I'll get a constant. Now, there are several functions where when you take the derivative, you get back to the original function. If this were mechanics, we'd play with this a little bit longer, and I would kind of steer you towards e to the xt or something like that. I'm not going to do that here because I think you guys, most of you, were in mechanics, and so I can take the exponential off the table because we know it doesn't work. And we're going to go with the trig function because that's another thing where I take the second derivative, I get back the original function. The derivative of sine is cosine, the derivative of cosine is negative sine. So second derivative gives me back the original function. And of course, I can pick cosine or sine, and it will still work. So I'm going to choose cosine, but it doesn't really matter which one of these we choose. The answer is fine for either one. So I think Q, as a function goes, is related to cosine with some number dealing with t. Now, because Q is in coulombs and cosine is a function, I will need to put something out here that represents when I have the maximum charge on something. So since we're talking about perhaps the capacitor maybe, I chose cosine because the capacitor would be at full charge at time equals 0, and cosine is at a maximum when the parameters in here are 0. Now, I'm not done. I'm trying to build a function. So I'm going to consider what does dq dt look like, and what was the second derivative look like. So I'm trying to build out what I think the function is going to be, knowing that this is my ultimate goal. So I know that if I take the derivative of cosine, I get negative sine. And I'm leaving that space there because something has to come out of my function eventually. And I know through the chain rule, anything in the parentheses is going to come out of my function when I take the derivative of what's inside the parentheses. Correct? You guys have done the chain rule before? So like I said, I am just guessing at what my answer is going to look like, but I have some good reason to do the guessing the way I'm doing it. I know when I take the next derivative, I'm going to get q, the negative sign will stay, and I go back to cosine. So I know this shell of a function is going to work because all of this portion is the original function. So now all I need to do is realize what do I have to put inside the parentheses so that by the second derivative, I have this term out front. And I think it wouldn't be hard to guess what that's going to be. I think it's got to be 1 over the square root of LC. Right? Because when I take the first derivative, I will get, obviously, the sign. That'll all stay inside, but due to the chain rule, I'll have to multiply this by the derivative of what's inside the parentheses, correct? And I chose the square root because I'm going to do this twice. So when I take the derivative again, I still have 1 over the root of LC. But now I'll have 2 of these out there. And their product will just be 1 over LC. Go ahead.
Why can't we just have the 1 over LC?
That is an excellent question. And I'm glad you brought it up. I wouldn't have thought to say something about that from the beginning, and I should have. So I appreciate that question. And you guys might not understand his question, and I don't know if I can restate it better than he did, but he said, why didn't we just start off with 1 over LC outside? Part of the reason we can't is because this is separate from that. If I did that, I'd have a 1 over LC over here too, and they would just cancel out arithmetically. But the other reason is actually more important, even though it's not really answering your question. You can't take the cosine of something that's in seconds. You can only take the cosine of an angle measure. So I have to have time inside the cosine because of the parameter of time being part of my derivative. But I have to multiply that by something that will render an answer in radians or in degrees, but we'll say radians. So I have to multiply it by something that's in radians per second. Does that make sense? Of course, we're just hoping that 1 over the root of LC is in radians per second. And considering all the different things that are in L and C, that would be an interesting proof for you guys to do on your own sometime. Or maybe we'll do it tomorrow because we'll run out of time today. But that suggests that this is a pretty strong candidate for our function for charge. Now, there's a lot of things to unpack here, but we were just guessing at an answer that fits the parameters. This is not the best way to do differential equations. And it only takes one change here, and you wouldn't be able to do that at all. However, there's something wrong with what we just did. This is how it can work, especially if it's a function this simple. There's also the possibility that there could have been a constant out here, some initial amount of charge that might have been in the system ahead of time. We'll just ignore that for now, not because we don't need it, but because it's immaterial. This function is sinusoidal, right? And moreover, it's not just sinusoidal. This suggests that the charge on the capacitor is going to be positive and negative, then positive and negative. It's going to go back and forth, right? It does more than that too. If you look carefully, this dictates how fast the circuit cycles, right? It will determine how close all the sinusoids are or how far apart they are. This circuit is tuned and oscillates. This is an electronic oscillating circuit, meaning we are oscillating current and charge in the circuit. Now, this will happen indefinitely, but let me hit the pause. And moreover, we can tune the circuit. It is tunable. So when I bring that up, that it is tunable, what I'm saying is outside, what am I doing, Mr. Shelton? You're a moron. You should be better. I try, but I'm just not that good. This is the angular frequency of our LC circuit. It completely determines the circuit. Now, you definitely should. You should go and prove that the units of this come out to be radians per second. Or better yet, it'll work out to be nothings per second because radian is a unitless quantity. But remember, angular frequency and oscillatory frequency are related. So if you take your angular frequency and you divide by 2 pi, you will get your oscillatory frequency. So if you want it in oscillations per second, this is how you build it. So right now, the FM dial starts at 85.7 megahertz and goes to 108 megahertz. If you want to choose, you could pick a capacitor and inductor that would oscillate in that frequency, and you can broadcast in FM. AM is in the kilohertz range. So if you want to broadcast in a kilohertz range, you do the same thing. You guys who are interested in potentially being transcending nerd, meaning some of you are just like passively nerdy, but some of you might want to become transcendent, get your ham radio license. That is a new level. People who build their own radios to talk to other people over those radios and see how far they can bounce signals from one place to another. Again, you just build a transmitter. This is the bare bones of building a transmitter.